Hey everybody, we wanted to take this chance to tell you a little bit more about gas stoichiometry, get some more practice with it. So we're going to do a second video here related to gas stoichiometry. If you haven't watched the first one yet, I recommend going back there because there's a good foundation there, and then you can pick up with the more advanced problems here. So when we're talking about gas stoichiometry, remember there's a relationship that we know about, which is that one mole of any gas, but it has to be a gas, is equal to 22.4 liters, but that's only true at STP. And so we can only employ it whenever we're at standard temperature and pressure conditions. But if we're not at STP, that value cannot be used. We can't touch it. So we need to do some other things, and that's what we're going to explore today. You'll notice in number one, you need a balanced chemical equation. I've given it to you here in the interest of time. And we're told some things, right? We are told that we have this arsenic 3 sulfide, and we have 89.5 grams of it. And by the way, this is a solid, so we're not going to be able to use 22.4 or any gas law stuff for that arsenic sulfide, but we will be able to use some gas law type things for SO2 because ultimately in the question we're asked for how many liters of SO2 we are looking for. You know this is stoichiometry because you're given one thing, you have to turn into something else, so somewhere along the line you need to convert to moles. Let's start with those 89.5 grams, right? We always start with what we're given. So we have 89.5 grams of this As2S3, and we know that at some point we need to get that to moles to convert to something else in our balanced chemical equation. So let's get rid of grams by canceling it out on the bottom, As2S3. We're going to turn that into moles of As2S3 because we know that from the periodic table there is a molar mass that allows you to equate grams to moles. For As2S3, if you add it all up, it's 246.05 grams for every 1 mole. And now that we're in moles of As2S3, we can go from moles of As2S3 into what we're looking for, which is moles of SO2, using the coefficients from our balanced chemical equation, which is a 6 for SO2, and it's a 2 for As2S3. And again, we're not going to simplify that just so we know where it comes from. So now, what do we do? Well, we're looking for liters, but the problem is this is not at STP, so we can't use 22.4. But we are told the different conditions that exist here, 20 degrees Celsius and 98.0 kPa. So what we can do here is solve this equation, and if you'll notice, when you cancel out grams of As2S3 cancel, moles of As2S3 cancel, you're left with moles of SO2, and if you do the math, you'll get 1.09 moles of SO2, and of course moles is our variable N that we use in PV equals nRT. We also have some other parts, right? We have pressure. In fact, the pressure that's given to us is 98.0 kPa. We're looking for volume. We are told that the temperature is 20 degrees Celsius. So if you add 273.15 significant to the ones place, you will get 293 K. And if you're a keen observer, you recognize that with PV equals nRT, kPa doesn't work for us. However, if you remember back to your whole year resources page, there are different R values, and one of them happens to have kPa, 8.314 liters times kPa. So let's use that one. That's going to make our lives easier. If you would prefer to convert this to ATM and use our normal 0.0821, feel absolutely free to do that. But in the interest of showing you a different way, let's do PV equals nRT, but let's do it with that different R value. So we have PV equals nRT. We know that we're solving this one for, let's see, what do we want here? We want volume, right? So if we're solving for volume, then V is going to be equal to nRT over P. We can plug in what we have. So we said that the number of moles we just calculated is 1.09 moles. That new R value we said is 8.314. And this one is liters times kPa, so it will cancel, over moles times Kelvin, times our temperature, which is 293 K. And then we're putting that all over our pressure, which happens to be 98.0 kPa. And when we cancel our units, moles is in the numerator and denominator of the top of the fraction, Kelvin is also in the same boat. kPa is in the very top and the very bottom, so we're left only with liters. That's great because we want a volume. If you keep your sig figs, you'll notice you want 3 sig figs, so your new volume is 27.1 liters of this gas, which happens to be SO2. So in that case, we obviously had to do P equals nRT at the end of the conversion after we had done a mole-to-mole conversion. But what if you had a situation like in number 2, and here we've already given you a balanced chemical equation, what if we tell you this information? So we want to know how many grams of silica, and silica, by the way, is SiO2. So ultimately here, we are looking for a number of grams of this. How many grams of silica are required to react with 2.65 liters of HF? So we have 2.65 liters of this. And we know we're doing stoichiometry because we are going from one thing to another. The problem is, this is not at STP. But it is at some conditions, right? We're told it's at 2.39 atm and 15 degrees Celsius. So what we can do with that is start jotting down our variables, right? We know something here. We know that we have a pressure, and our pressure is 2.39 atm. We were told a volume of HF. It is 2.65 liters. We were told a temperature of HF where this is being measured. It is 15 degrees Celsius plus 273.15, significant to the ones place is 288 Kelvin. We know R. We also know that N is our unknown because if we can get moles of one of these things, we can convert from moles of one thing to something else using stoichiometry. So that means we can do ourselves a PV equals nRT problem, but this PV equals nRT problem is going to happen before our dimensional analysis, and we're going to solve here for N. So N would be PV over RT. When you plug in all of that, you'll be left with a pressure on top of 2.39 atm, a volume on top of 2.65 liters. You'll have your R value, which because you're using the pressure ATM is going to be 0.0821 liters times ATM over moles times Kelvin. And you're multiplying that times your temperature, which in this case is 288 Kelvin. So you want to cancel units. You'll notice the very top has ATM, and down here there's an ATM, liters on top, liters on the bottom. In the denominator, there's a Kelvin on the top and a Kelvin on the bottom of the denominator. And here we see 1 over moles. So we multiply by the reciprocal, and we get that N here is equal to 0.268, so 0.268 moles of this gas, which we said is HF. So now that we have moles of HF, we're in a great spot, right? Because if we have moles of HF, that can be the beginning of our stoichiometry problem. If we have moles of HF, it's very easy to convert to moles of SiO2 using the coefficients from the balanced chemical equation. We know that moles of HF needs to go in the denominator to cancel out. We know that we're looking for silica, which is SiO2, and the balanced chemical equation has coefficients that were given to you of 4 for HF, and if there's no coefficient, it's a 1, so 1 for SiO2. So this is a 1 to 4 mole ratio. And once you have moles of SiO2, that's all well and good, but you'll notice the question asks for grams. Because this is a solid, you have to use the periodic table, and it turns out that 1 mole of SiO2 has a molar mass of SiO2 that you could calculate using the periodic table, but I'll tell you it turns out to be 60.09. Once you've done all of that, your moles of HF cancel, your moles of SiO2 cancel, you're left with grams. And at the end of the day, with appropriate 3 sig figs, you will get 4.03 grams of SiO2 for your final answer. So hopefully you enjoyed this kind of exploration of a little bit more complex stoichiometry problems. As always, as soon as you can convert to units of moles, you're in a really good spot for doing stoichiometry because you can convert from one thing to anything else. And bear in mind, we could get tricky, right? We could give you like a limiting reactant problem to do with gas stoichiometry. So there are a lot of different avenues you can take, and they're all exciting and fun.